Okay, thank you very much, Rachel. In fact, actually, before I go into the details, maybe let's unmute the room because I actually have, first of all, I don't know who is really in the room. And so I'm wondering whom of you has actually worked on or worked with the plane wave DFT or DFT in solids at all. And I think probably the best way to do this is that you people in the room raise your hands and Rachel kind of gives me an impression through the line back because otherwise I'm not going to see this.
Great. I turned the camera on, but I think it's at a not so helpful angle, and I couldn't
Yeah,
figure
I
out where
don't
the
I don't
controls.
think so.
Okay, I couldn't figure out where the controls for the camera were, so I'm just going to turn that off. All right, so by a show of hands, and I will report the results back. Have you run plane wave DFT before? I think is basically the question.
Yes, indeed.
I would say that's a large chunk of the room. I would say that might be like 2/3, if not more like 3/4 of the people here in person.
Perfect. Yeah, okay, great. This was just to make sure that I'm studying at the same level. Okay, great. So if you want, yeah, please mute again. So thank you all for being here. And of course the big thanks goes to Rachel for having spearheaded this meeting. And indeed I'm very happy this is finally taking place. I mean, many of us have worked in some or another way on the packages that are involved on building the community. And so Rachel is now fortunately, yeah, stood up to organize this, and I'm personally very sorry that I can't be there in person. I mean, yeah, for some various teaching and other commitments, it just didn't really work out. But I'm more than happy to do this remotely. And part of doing this remotely, of course, means that it's really tough for me to get a feeling what's going on your end. So the way I've set this up is that I first, maybe for half an hour, give you a bit of a presentation of just an overview of what DFTK is and what kind of interesting research questions you can tackle with this code. And then I will indeed go more towards the hands-on, the live coding type presentation of various features of some things you can do. And please go ahead and interrupt me at any time. I know this is potentially not so easy with your microphone turned off and things like that. But I mean, since I don't have a way of seeing your faces, the only way for me to understand if you are following or not is if you ask questions. So I do really depend on you to stand up whenever something is not clear.
I'll interrupt you for just a second. Just say I'll try to sit in an angle where I can see everyone in the room. And if there's a question that someone wants to pass on, just raise your hand and I'll jump up and unmute so that you can ask the question. I think the room mic should pick everyone up okay, so you should be able to ask your own question. So yeah, I will sort of spin around and face the room and just throw your hand up, and I'll interrupt Michael for you, so you can have a chance to ask a question if you need to.
Thank you for being the ears and eyes in the room. Thank you. Okay, right. So indeed, so today I want to talk about DFTK and in particular, like our interdisciplinary way of doing DFT calculations. So as you see here in this nice image that we made a few years ago, the goal of the code is really to bring together people from material simulation, from mathy topics. Back then I said numeric analysis. Now I would probably also add statistics here. People who work on scientific models and people who work on HPC. And some of the sort of the flagship results we got over the past years is methods that, and if you want, like self-adapt the iterative algorithms of DFT to the models, to the problems that you have at hand automatically, and some directions towards error control, meaning you are able to estimate errors of your calculation in a more or less rigorous way. And so the main motivation for doing a lot of this is in particular materials discovery. So as many of you probably know, and here I don't want to spend too much time, a lot of the problems, so to speak, that we have, talking about automation, talking about materials for batteries and so on, that's something where fundamentally DFT simulations are used. And why are they used? Because experiments are expensive. In particular, if you think just about the spare figure that I like to quote, that one fume hut takes about as much energy as 3 to 4 households. three households, you clearly see that, just doing experiments are not going to help us. And so, as you know, what people do nowadays is high throughput screening. So we have basically materials that we know can be represented in some atomistic structure. We know how to do the computation on some computer, on some supercluster, and using the properties that we predict, we can say, okay, is this a useful material for example, improving it in terms of solar cells or in terms of batteries and so on. And the energy consumption of such a computation is considerably lower. So, here I'm just showing a lump of silicon. You can probably believe me that maybe within 4 hours of a standard CPU, or here 8 hours of a 36 core processor, that's something, you can do already quite a lot of DFT simulations. And that's that cheap in comparison, basically. Now, the key thing is automation. And basically, we can do this at a larger scale, but this is where the problems also start, right? Because basically, as soon as we're moving up to something where we're simulating tens of thousands, maybe a million of compounds, in order to basically, in these multi-step procedures, filter out only a few compounds that we eventually make in the lab, we're starting all of a sudden to hit another wall. So here, for example, I'm showing, I'm just showing the usage statistics of the Archer 2 supercomputer. And basically, I've cutting here the statistics in February 23, but believe me, it doesn't really change very much if we move on until today. So overall, the blue bit here is periodic plane wave DFT. This basically makes about a third of the supercomputer usage, and 50% if we include all kinds of electronic structure or quantum computations. So clearly there's a lot of computation going on, and we're basically back to the problem that computing also is not necessarily cheap in terms of energy. So for example, this is the Lumi computer, one that we use, that we participate from from Switzerland. And basically just running this takes about 1.5 EPFL. So 1.5, the entire energy usage of EPFL is the Lumi supercomputer per year. And this is, basically 14,000 households. So it feels a lot like we've not made too much progress. And in particular, we're basically to the problem that now there's a complexity of setting up these calculations, right? We now have a lot of parameters to choose. All of you who have worked probably with some sort of electronic structure code know that there's a lot of things you have to tweak in terms of algorithms, tolerances, models. And even though there's a lot of software out there that tries to automatize these things, there's still a lot of problems. And particular at the level of electronic structure computations, questions like how can we really optimize the energy usage to get to basically the predictions that we care about? How do we know how much accuracy we actually need? And in particular, alluding to what Rachel has mentioned, talking about algorithmic differentiation, does this give us some tools which are interesting to explore? And this is basically the goals in my group and the goal of DFTK, to really come up with ways to, for example, how can we, for example, indicate errors in computations? How can we use this in some way to automatize and verify calculations? How can we do some active learning, and so on and so forth? So the point why I'm showing you all of this is I'm trying to convince you here that there's many factors going on in modern, interesting material simulations. We're no longer just talking about the physics. We're often also talking about mathematics. We're talking about statistics, numerical analysis, uncertainty quantification, and basically there's really a lot of expertise that goes into running these things, and a lot of different expertises at different levels of science. And so basically the big problem, the big issue here is that somehow we have now multiple communities that do need to work together, because after all, this is really the research questions at hand. And basically all of you who in some way or another might work in interdisciplinary sciences know that there's a lot of issues that just come inherently from the different conventions, from the different language that people use. And in particular, one or a few things I want to highlight is what I typically call the speed of research problem. So I'm in mathematics and material science, and I can tell you that in mathematics, if a PhD student publishes maybe a paper a year, that's kind of okay. However, if in a material science you do that, that's considered not such a good PhD, right? So my point here is that just because of these different expectations and how research moves along, people structure their research differently. And in particular, in some sense, the software that is used to push this research and do this research, that also has a slightly different structure as a result of these different cultures. So in particular, I'm again contrasting mathematical software and software from the application side. So in math, people typically talk about numerical experiments. They talk about reduced models. They talk about things like really high-level languages. And in the end, if you write a paper with the software, then you're sort of done with it. I mean, very little. I mean, that's not. I'm very much generalizing here. Of course, it's not universally true, but in the end, software is around to showcase that some idea you have really works on a limited test case. However, clearly on the application side, what we really want is we want to model the physics. We want to basically be able to go as fast, as big as we possibly can. And therefore, codes are bigger, right? Performance is certainly important. And also codes go over possibly hundreds of man-years of development, right? So clearly, the point is that the spirit of how you really approach a software project is very different. However, in order to be really able to work together, these things can actually be a bit of an obstacle. So for example, clearly different codes with these different characteristics need different skill sets, different communities, different kinds of developers. And as a result of this, because you have these different strands of code, also the knowledge transfer is often inhibited, right? So mathematical methods that come from this experimental side of programming, they might never actually be tried in an application setting, simply because, you know, that's not really where the math codes even apply. And in particular, in the other direction also, if there's some, you know, challenging material, let's say, that are really tricky to model, the math codes may not even get to the point of being able to model it, simply because they just don't scale to the size of the material, for example, where the problems actually come about. So what I'm trying to say here is that coming up with a way to overcome these obstacles and having people work together in software, this is something where I think considerable innovation can come from. And there I'm coming back to, as Rachel said, a quote there where I'm paraphrasing Alan Edelman. The hypothesis here of DFTK and of a lot of the work we've done over the past years is that people compose as software composers, right? So basically, we first need to put some sort of an emphasis on coming up with codes that are able to combine communities, in particular in DFT, for example. And then as a result of this, people can jointly work together on scientific projects that are otherwise difficult to achieve. Okay, so this is sort of the prelude. And maybe before I make a small pause for potential questions, let me just tell you that this has really been the motivation for the density functional toolkit. This is sort of the state where we are right now. Basically, we've come up with a code of something like 7,500 lines right now. We can treat problems on the size of 1,000 electrons, so there is some parallelism for MPI. We have a fairly standard set of models. So if you know about this, we do meta-GGA functionals. We have norm-conserving pseudopotentials, fairly standard. We can do response calculations. More recently, we have been working on integration with high-throughput engines. So these really engines that can handle and orchestrate these tens of thousands or potentially more of calculations. The goal is really to be able to try ideas in simplified settings, something where mathematical approach could be really developed and tackled, and then in the same code be able to sort of scale it up to something where you can really test it on in automated calculations on a few hundred or thousand test cases. Why is this possible, or how is this possible? Clearly, the ability to integrate with what Julia already has to offer has been quite crucial there. I'm talking in particular about HPC tools like MPI, to a lesser extent GPU. That's something we have worked on, but the performance is horrible, so please don't try it in practice. but I would be very happy to support you, or if you're interested, let me know to basically move this further along. AD is something I will show in the demonstration later. And yeah, there's actually been quite a lot of people from outside sort of our collaborative circle who have contributed, including undergrads in particular. So the code is really out there and it's open, and hopefully by the end of this demonstration, you will also see a little bit how to use the code in practice. Okay, so this is, I think, a good moment to stop for a first round of questions, if there are some, and then I go a little bit into some of the things we recently did with DFTK.
Any questions in the room? Yeah, Ray, go for it.
Hey, hi, Michael. Ray here. I have a question about the precision you mentioned. I see 32-bit is more than 64-bit. What's the rationale to go bigger and bigger? Do we need that precision for DFT? And because
yeah,
you mentioned, sorry, go ahead.
Yeah, that's a very good question. So why do we want to do this? How do I best? Okay, so let me go back to this image here, right? You see these nice error bars that come from basically a mathematical treatment of the numerical error and some reduced problem of silicon. So actually what we did there is we included the error from the plane wave basis set. We included the error from solving the, basically diagonalizing the Hamiltonian in this case, but we also included the error from the floating point computation. So to come back to your question, why would we be interested in this? The answer is to know what we're doing wrong at 64 bits. So usually that's not relevant, I have to be frank with you, but it's something where we wanted to say, well, you know, in case we care, we can actually track these things. And the nice thing is that with some floating point types that are available in Julia, for example, the double floats floating point type, the performance malus that you get is not that bad. It's actually less than a factor of 10. Which means that, you know, even though you may not be able to do your entire DFT computation at this elevated floating point type, you can do sort of your checks, right? Sort of to check that what the solution you have actually obtained is the right solution. That kind of checks for the residuals, if you want, and so on, that you can do at elevated precision very easily in DFTK. So it's in some sense just a way to be safe. And let me just add that indeed there are use cases where elevated precision is important. So in fact, actually just very recently, a few months ago, we pushed a paper on arXiv where we do Concharm inversion. So we sort of go the other way. We go from from a density back to the potential. And there it turns out that you can get into numerically very challenging terms where elevated precision is crucial to actually give you some numerically meaningful answers. So that's a little bit why we try to go down this route of being able to support elevated precision. Not so much for standard DFT, but more for, let's say, unusual use cases that with Julia we are actually able to tackle. I hope this answers the question.
Okay, all right, unmute it again, go ahead.
Thanks. But I also see the kind of the conflict of interest of pushing for the GPU computing, where people are actively trying to reduce the precision so more data can be communicated at once. I don't have any idea or thoughts on that.
But you know, you make it sound like it's one or the other. Why can't I have both?
Good point.
Jason.
Hi, Michael. Jason here. What is your vision? Like, there's also like a more commercial one. So, your vision about DFTK is more like quickly modeling, or you are also DFTK is like in the future can be the not replacement, but also compete with this commercial, not commercial code, but more the code DFT code that are being used.
Yeah. Some of it, I think, will become clear in the second half of the presentation, so I'm gonna not answer that. But with respect to commercialization, at the moment, to be completely honest with you, I see very little immediate possibilities. And the reason is because of this, okay? 100 man-years of coding that went into the existing commercial packages that means in particular a huge set of features. And I don't have to tell you, Jason, how important it is, right? That you are able in practice to switch between one kind of pseudopotential, one kind of DFT model to another, and making actually all of these available in DFTK plus an adequate performance and so on and so forth. That's a huge amount of work. And I mean, given like even all of us in the room there in Pittsburgh, plus the people in my group listening in, plus the others, you know, who are on the call, if all of us worked on this for a year, I don't think we would be able to get to that point. So I think one has to be realistic. And DFTK, I really see it more as a tool for coming up with new algorithms, with new ideas that are able to basically provide new methods that are simply really tricky to do in practice in other codes. And in some sense, I see it as a complementing tool, not so much as a competition to existing codes. And as a result of this, commercialization, maybe in the future, but not right now. Yeah, and where it should go, I think basically trying to come up with better methods and trying to sort of understand errors in a way that potentially the results could be useful also in other contexts and in existing codes. Yeah.
Any other questions either in the room, or I don't see anything on the Zoom as
Great.
yet.
So then I guess I move on. Yeah, so what have we achieved so far? So first of all, if you have never seen DFT, just a bit of a sort of introduction of the notation that I will also use a little bit later in the demonstration. So the whole goal of DFT is to understand electronic structures. And what we're able to do is we're coming up with a single particle model. So something where, you know, you have a Hamiltonian, that's the thing here in brackets, you diagonalize it to get eigenstates, and then those eigenstates, again, you use to build up your density, which is part of the definition of the Hamiltonian. So the point here to just show this equation is to say it's a nonlinear problem, it's a nonlinear eigenvalue problem, a nonlinear eigenvector via the density eigenvector dependent eigenvalue problem. And this is essentially what one solves in order to get the DFT solution. And another way to write it is a self-consistent field problem. It's a fixed point problem. So the idea is you put in a density, you get a potential via this equation here. Then you diagonalize the Hamiltonian from the eigenstates, get a new density. And if the density that comes out is the density that goes in, then you're done, right? That's sort of the goal of DFT, written in a compressed one-line form. And typically the way people solve it is that they do this so-called damped preconditioned fixed point iteration. So here you just have one update step, essentially one step of this SCF that I just sketched. You have some way of preconditioning, modifying essentially this update and some time step. Okay, so I just wanted to show basically the structure of the problem that we are interested in solving. And many of these parameters are actually chosen by trial and error. So here I'm just showing an example for the damping parameter. So here is a few cases which are not so easy to model. So this is a gallium arsenide supercell. This is a Heusler alloy. So an alloy which is a so-called half metal. So in one spin channel, this is actually a metal, in another it's an insulator. So from an electronic properties point of view, a very complicated system. And as you see, this is also reflected in the damping choices. So basically here you see the convergence with a number of iterations, a number of Hamiltonian diagonalizations. And the color code gives you the damping parameter that is chosen. And just by looking at the colors, you see, well, it's very irregular. You know, somehow some colors work very well, some dampings work well, others don't, right? So the point is that the usual heuristics that people come up with, namely that you sort of, you know, just change the damping, make it smaller in order to get convergence, that doesn't always work so well, right? And so these kind of settings are the settings that we are interested in for DFTK, because those actually trigger some interesting mathematical research problems. And indeed, this is what we have done. I don't want to go into too many details here, but essentially what we came up with is we came up with a procedure that automatically chooses the damping based on some line search idea. And as a result, still for these complicated system allows you to get a very nice and regular convergence. And similarly, we came up with a preconditioner that actually adapts here to the systems under study. That's something we will look at in the hands-on approach later. So the goal of these preconditioning techniques is really to make sort of less, like to put less of the choice into the hands of the user, but more basically have methods that are able to automatically adapt to the type of systems you have at hand, right? So that's just basically giving you two ideas what we have done. Something we more recently looked at is the question of property calculations and response theory. So here the point I want to get across is if you have solved, for example, such an SCF problem, essentially what you're saying is I have some fixed point density given some parameters of my model, which therefore actually defines an implicit function of the fixed point depending on the parameters of the model. Okay, so parameters of the model, what could that be? Well, it could actually be something like atomic positions, some external electric field, or some other external parameters that I might apply to my system. And why is this interesting? Well, I mean, if I want to understand how my material changes under external conditions, this is exactly what puts me into the realm of property calculations and into the realm of making a connection between theory and experiment. So basically, this is something that we have looked into substantially over the past year or so. And in the end, what helps is that this makes the computations of properties faster if one is able to solve these kind of problems faster. But additionally, this is also related to algorithmic differentiation, because these parameters here, they don't necessarily need to be external. They can also be parameters of, for example, the pseudopotential or the model. And therefore, in this way, by being able to compute derivatives of the density on such parameters in a generic way, we are basically able to, not just compute properties, but also compute any derivatives via algorithmic differentiation very fast. Another way to use algorithmic differentiation in our code is basically to be able to save code. So for example, maybe you guys know that the stress is typically defined as the derivative of the energy with respect to some, if you want, some strain here, so some distortion of the lattice. And typically the formula to implement this would be this. And in fact, actually what we do in the code is very similar. Okay, so if you want, you can almost do a one-to-one translation of the formula to the code. And this is essentially our computation of the stress. And just to be very clear here, I'm not cheating, at least not very much. So in the end, what I'm showing here, what I'm highlighting here, this is really the implementation that we use for the stress computation in DFTK. Maybe I'm making it a bit bigger here. So in the end, it's really, we have some function to recompute the energy. We have some way to use the fact that there's some symmetry in the stress tensor, so we can actually only compute 6 components instead of 9. And in the end, the main thing that kicks off the stress computation for us is a call to forward diff.gradient. So really, I mean, these 30 lines of code are very generic, and they do indeed compute the stress for pretty much all of the methods that we have available. There are some caveats. I'm happy to talk about them in questions, and if you're interested. So it's not all perfect here, but basically we're getting very far with very few lines of code. That is essentially the point. And then I should also say that this was like the initial groundwork for this was done in a GSOC project. We've moved on from there. But again, trying to show how with AD you can actually get very far, sometimes and save code in particular. So back to the question of computing derivatives of the density, of the fixed point density. So the point to make here is that in the end, in order to compute these derivatives of the implicit function, you use this implicit function theorem, which means that the first order change of the self-consistent density with respect to some external parameters comes down to this equation. Just believe me that this is true if you've never seen this before. In the end, it's something that people typically call the Dyson equation. And the way to solve it is that one uses some iterative inversion for this object here, which in the end turns out to come down again to some equations which are called the Sternheimer equations. So why am I telling you all this? Well, the point is that if I want to compute the derivative of the density with respect to arbitrary parameters, so in other words, if I want to be able to do AD through density functional theory, then I need to be able to solve these equations fast. And every time I need to solve equation 2, I need to apply this operator 1 minus k0k a bunch of times, say 20 or 30. And each time I apply this operator, I need to solve yet another n equations, which are called the Sternheimer equations, okay? So if I'm not able to solve these two things fast, AD in density functional theory basically is not possible. So we've worked quite extensively, and again, I don't want to spend too much time on this, on really improving here using some mathematical insights, the performance of the Sternheimer solver and the outer Dyson equation solver in DFTK, and we've been able to really reduce quite substantially the number of iterations of Hamiltonian applications that are needed. So the point to get across is that by actually having a code where you can really look into the numerical details, you're able to come up with algorithms that you can then integrate and make things such as algorithmic differentiation really happen. So basically getting this performance is crucial in order to be able to not just, write it down and wait for it to compute, but to be able to actually use this on real systems and challenging systems such as this Heusler alloy that I'm showing over here. Okay. Let me maybe pause at this stage and see if there's any other questions on the aspect of AD before I move on to another point about error control.
Not seeing any hands up in the room. Last call. Don't see anything on Zoom either, I don't think. So I think you are good for now.
Great. Okay, so now the final thing I want to get into is the question of error control. So I mentioned that this is something we were also interested in, and the main point I want to get across is errors come in different flavors, right? So we have the typical error that we think about in materials modeling, that we have different models, right? So we have models that, for example, hybrid DFT or even beyond DFT that are super accurate. And then we have models that are basically, Hartree-Fock, or I don't know, for solids is not very accurate, clearly. Or, maybe even more reduced models, something empirical, that those are typically not giving us a very detailed physical insight. So something where we only see gray instead of the real colors. But then typically we also have another axis, which is the kind of the basis set size that we choose. So if you want here, the sharpness of the computation. So usually we don't necessarily care about getting the highest accuracy numerics when our model is bad, and clearly also we don't care about using beyond DFT quality if we only are able to afford a small basis, right? So the point is that somehow we want to be in the middle, but which middle is ideal is not always so clear, and this is something where error control can really help. And I mentioned already that we've worked quite a bit on this. So this is the example I explained earlier. But more recently, we also started looking into questions related to can we estimate the basis set error? So here, if you're familiar with this, the ECAT parameter is basically in plane wave DFT, the parameter that gives you the size of the basis. So basically, the higher the ECAT, the larger the basis. And here what we're doing is we're basically plotting the error, which is estimated by, comparing against a really accurate calculation with some error estimate that is computed at pretty much the same cost as the SCF itself. So basically for twice the cost of an SCF, you can now estimate an error, which according to this regression curve, that you see here scales fairly well. I mean, correlates very well with the real error. So why is this interesting? Well, I mean, if I know the error, and I know I'm able to compute it at about the same cost as at the SCF, I can also start to reduce computational cost, meaning I can sort of squeeze more out of the numerics that I have, but I can do it in a way that I actually know what is the accuracy of the resulting code. So this is something where DFTK has actually been quite an important research tool over the past years. And what we are trying to do now is we're trying to actually use these error estimates in combination with machine learning. So in order to be able to really inform a machine learning model of the quality of the DFT data that it gets. And this allows one to actually go a bit beyond what existing what existing machine learning models can do. That's at least the hope. And so here I'm showing a very, very naive and a simple example that Anna Paulisch, a PhD student in my group, just realized very, very recently. So here what we're doing is we're just fitting an equation of states with a GP, nothing super fancy. But what we're doing deliberately is we're basically having less high level, high accuracy data on the left than on the right, but we're allowing ourselves some low accuracy data, so data where the basis is basically not perfect, it has some errors, but since we're able to estimate the errors, we can give those to the machine learning model, and the green model here is able to use all the data and the error estimate, and it does substantially better than the orange and the red model, which basically is not able to use the error estimates to improve its predictions. So that's just one thing where I want to show you how sort of this idea of error estimates fits in. Okay, another thing we did is we looked into questions like how do, for example, the density of DFT calculations change when we change the pseudopotential parameters. Basically the state where we are at is one is able to compute small sensitivities, so basically derivatives of the density with respect to the pseudo parameters. And that's something where this algorithmic differentiation framework that I was sketching really comes in. Okay, more recently, as I mentioned, we are moving towards DFT and AIDA, and basically this is something where Bruno Plumans, another PhD student that started in my group recently, is working on. We're trying to really make it possible now to run DFTK from in a high throughput workflow manager in an automated fashion. Okay, so this is, I think, another good place to stop for a few questions. And then I'm wrapping up and go to the demo afterwards.
Last call, either in the room or on the Zoom for any questions so far. All right, carry on.
Great. So yeah, just to finish this off, I have still an open postdoc position if somebody's interested. We have a workshop, Julia, for numerical problems, but actually the deadline for registration has passed. So if you have missed it, unfortunately, that one is full. Yeah, and basically this is a summary of the things that I briefly sketched. Something where I would be very interested to talk to people is GPU and GPU performance. So if somebody is willing to work on that, there's definitely a lot that we can do. We definitely have still some issues on the general integration. I will show you basically the state of the art in just a second, but definitely here, like bugs and documentation is missing. And I would be very happy if you're curious on this to work on this during the hackathon or something similar. Yeah, so basically everybody who is involved is here on the slides. I mentioned Bruno, I mentioned Anna. Niklas, I didn't mention. He worked a lot on this question of algorithmic differentiation. This basically this stress implementation that you saw goes down to his work. Cedric is a leaving postdoc in the group. He's worked a little bit on using AD for materials design. I didn't present about this today, but yeah, this is my group. And if you have more questions, I'm very happy to take them. If not, I think I will move on to the demonstration part.
I think you're good to charge ahead.
Great. All right. So before I get started, let me first mention the sort of the key things of DFTK. So probably almost all of you who have heard about DFTK went already to dftk.org. This brings you down directly to our GitHub repository. I think the second most important thing is our documentation, docs.dftk.org. Basically, a lot of the things I will talk about for the remainder of this talk come from examples that are on this page. So in particular, Rachel already mentioned the tutorials. So this is sort of the hello world. We will also go through this in just 1 second. A bit like if you're not very familiar with Planewave DFT, there is a background section where there's plenty material to get started with DFT and Planewave DFT. There's basically a prior school that we did with like selected material from there. Some nice papers that are worth reading, in my opinion. And in particular, let me switch to the dev version, which has all the updates. In particular, I also gave a 30-minute introduction to DFTK that has been recorded. That you find here, along with the slides and the Pluto notebook, and also various other talks at occasions that have happened in the past. Here, and sort of following up on the background, there's like gentle introductions into Planewave DFT and some exercises for you to walk through if you're interested to learn a little bit more about the math and the theory behind it. That I'm going to skip for today because I felt, you know, from the discussions and also from this show of hands I did earlier, that basically most of you are familiar with this part. The next section is really more about running DFT calculation with DFTK. There I'm going to do a few things in this hands-on, but there's definitely more things worth checking out. This is sort of the basic toolbox, I would say. A few more sort of advanced things about response properties, questions about ecosystem integration, so atom space, atoms calculator, and so on. ASE, I will talk about this a little bit later on. And then further on, more details about solvers, about non-standard methods, so something more mathematical inclined people will probably be interested in. Some things that recently were done where basically these error bounds that I showed on this one correlation plot, how they were computed. Here's basically a proof of principle implementation for that. It's not very usable at this stage for basically end users, but we're working on this, and there will definitely be some updates very soon. Okay, so this basically gives you an overview over the DFTK website. And with this, I think we are in a good position to finally get started on the hands-on part. So for those of you, I'm not sure if Rachel has merged my pull request. Let's see if it's been done. Maybe not. So for those of you who want to have a look at this material later, so if you go to my GitHub account,
it, Michael, maybe like 10 or 15 minutes ago. So you might just have a cache thing, but hopefully other people who load it now will be able to get it.
Yeah, maybe it's not yet updated. In any case, if you go to my GitHub account and then demo molasses-I workshop DFTK, then there's a rendered version of the notebooks. I will code them live, but if you're interested in some of the results, they are already on there. And basically, this also has the presentation that I just presented. So everything I'm going to talk about today is in here. So demo molasses-I workshop DFTK has all the material.
And I'll just mention briefly for those of you who are newer to Julia and who were at the workshop yesterday, we did most of the demos in Jupyter notebooks. Pluto is a Julia-only notebook system. It's similar to Jupyter in many ways, different in some other ways. If you're curious in learning more about that, I'm happy to talk over lunch. But if you'd like to code along, you can go ahead and install Pluto. In principle, it shouldn't take too long, but what might be even faster is just to copy the code from the cells in the rendered version and perhaps just run it in your REPL, and then all you'll need is an environment with all of the same packages that Michael has. So that might be the quickest way to get started if you want to follow along. Like I said, if you're interested in learning about Pluto, happy to talk about that over lunch, but I don't want to derail things and take too long getting absolutely everyone set up with that, because it can be a little bit different on different platforms, as with many of these systems. So if you want to just sort of follow along looking at the code and watch Michael do it, that's fine. If you want to run things, that's also great, but just copy pasting the code if you don't already have a Pluto installation might be the fastest way to get up and running. Would you agree, Michael?
Yeah.
Okay.
Yeah, I agree. So in fact, actually, if you at some point want to run these things, later, the easiest way to do it is probably to just go on the website, click on, for example, a notebook that interests you. And then when you here on the top right, you have edit or run this notebook. And here you really have a step-by-step instruction that tells you how to basically get started. So if you just install Julia and Pluto, so by running sort of these two commands, you will be presented with a screen that basically looks exactly like this. And then if you just copy what this one is here and paste it in the path and click open, then it will actually just download and run the notebook on your computer. So in that sense, these, I'm just going to repeat it again. If you just click on the website that is here, you click on one of the notebooks, edit or run this notebook, and here you have the step-by-step instructions that allow you to actually get started. And that is all you need. So the environment of packages will automatically set up. Okay, so let's get started. The place to get started in DFT, in my opinion, is Silicon. So Silicon is the hello world of DFT codes. So the first thing we want to do is we want to actually build a Silicon system. Here, Timo already mentioned the very nice Atoms Builder package by Christoph Ortner. So if I just do bulk of Silicon, I immediately get a flexible system with a Silicon structure. Basically gives me here the atomic, the unit cell and the atomic positions. And this is something I can directly use to run a DFTK calculation. In this particular case, what I will do is I will actually attach pseudopotential information, which means that I'm telling DFTK that it shouldn't use a Coulombic interaction between the silicon core and the electrons around it. This is done mostly.
Michael, we have a request in the room if you could zoom in 1 or 2 ticks.
Yes, of course. Better?
Everyone in the room? I'm seeing some thumbs up. All right, thank you.
Sure. Yeah, so let me just try to do it like this, then it's easier to see. So we're just now we're just setting up this bulk system, and we're attaching pseudopotential information. That is to say, we are telling basically we're adding information to the atoms in the abstract system. I should do it like this. So if I now, for example, inquire the information of the first atom, I see that now there's a property which has been attached to the atom, and this gives exactly the precise path to the UPF pseudopotential that I'm using here. So if you're wondering about these pseudopotential information, there is something which we call the pseudopotential library. Julia Sim pseudo library, and this has some information how to get these pseudopotentials and make them work. I'm not going to go through this, but I'm going to paste the link. So there you have the link for later. Okay, so the point is we now have a system, we attach pseudopotentials to it. So now we're ready to go for a calculation with DFTK. And what we typically do there is we set up a model. So for example, I'm going to use a PBE model here. I selected a PBE pseudopotential. So then I'm also using a PBE model. So I'm just saying model PBE of silicon. And this will set up a model with an exchange and exchange functional from PBE and a correlation functional from PBE. It automatically reads in the information from the system here. So it uses basically the lattice, converts it to atomic units, because in DFTK we use internally atomic units. It has also detected the pseudopotential information, basically prints some other details just for basically for information. And in particular, it tells you which terms are being used. So in DFTK, the Hamiltonian is very flexible. You could, in principle, set it up completely as you want. In this particular case, we basically have used, if you want, like a function that templates already a PBE type Hamiltonian. So it automatically adds some kinetic energy, some interaction of electrons with nuclei, some non-local interactions that come from pseudopotential. It basically adds something that describes the repulsion of nuclei from each other. Something that again comes from the pseudopotential to correct this repulsion here. And on top of this, some electron-electron repulsion, the Coulomb or Hartree term, and then the selected exchange correlation functional. We could do other things. So for example, there's also a slightly simpler model. So here, if I just compare model atomic and model PBE. So now, doesn't like it that so here basically, we can just have them. So this is just model atomic and this is model PBE. And you see basically the model atomic doesn't have these two last terms. So basically this is, this is just a bare atomic interaction without any electron-electron interaction. So this is something where you would assume basically non-interacting electrons. Anyway, it's not DFT, but I just wanted to show you that essentially very easily you can come up with your own models and use them in case you really wanted to. Like, for example, I think somewhere in the documentation we use also plane wave DFT to model the harmonic oscillator if you want to. Okay. So this is the way you set up the model. You can use some atom space compatible structure and just pass it on to a PBE model, for example. Then the next step is to discretize the model. So there we use typically a plane wave basis. So we pass the model to be discretized. We specify the plane wave basis cutoff. So this is, as I said, the parameter which essentially determines the size of your basis. So I'm just going to be very crude here and just use a cutoff of 20. Then the next step is to determine the number of K points. So in plane wave DFT calculations, essentially there's two kind of axes of discretization. The one is the number of supercells that you're essentially treating. That is sort of the number of repeats that you're implicitly treating in your problem. That is essentially this K-point parameter, and the ICAT parameter is something that determines the size of the basis. So here I'm just going to use 4, 4, 4. So 4 in each direction. If you're curious about what these K-points mean, this is exactly where I would point you to the background part of the DFTK documentation. This periodic problems section, for example, has, and the modeling atomic chains, for example, these two sections have some details on what these K-points mean and where they come from. Okay, so here we have set up a K-point grid and we have set up our basis. So now we are able to actually solve the DFT computation. So this we're going to do using the self-consistent field method. So CFRES. So basically here we're just passing on the basis, and the self-consistent field method automatically sets up a density, an initial density guess. it basically uses some algorithm based on this hybrid mixing, this LDOS mixing that I briefly mentioned in my presentation. And based on this, it automatically performs a DFT calculation and converges after a while. And based on this, we can now do some post-processing. So for example, we could plot the bands of this computation, which I can't because I did not include the plots package. So now let's quickly install the plots package, hopefully quickly. Yeah, plots is one of the packages that installing is not so super quickly. Okay, it's done. And now this should automatically disappear. Yes, very good. And I did something which is deprecated, so let's not do that here. But you see, at least it works. Okay, so you compute the bands, and based on this, you plot the band structure, and here it is. All right, so this is basically the one hello world example of running DFT computations. I'm happy to move on, but I'm also very happy to answer questions, curiosities, anything that comes to your mind.
Yes, Christoph, go for it.
Why are the pseudopotentials not integrated in the library, but as sort of something the user needs to download and pick out?
So they are integrated in a library in the sense that the artifact is automatically downloaded, but you mean why it's not hidden? Why do I have to see all this gibberish here? Is that what you're asking?
That's exactly the question.
The reason is because nobody's had the time to do it. So I have actually a sketch of this in my head, and I started working on this. Yeah. And in fact, actually, what's even worse is that there's even some really annoying artifacts, Tommel, that I completely hid from you, which makes this even more annoying to work with. So yes, that definitely should disappear. I agree 100%.
Other questions at this point? Anyone trying to follow along and running into any issues? And maybe try to troubleshoot very quickly. Okay. Don't see anything else here, so carry on, I think.
Perfect. So now the next thing I want to do is I want to talk about iron, because I think the next step here is to basically start modeling iron. So let's again start from bulk iron, which has one element in the unit cell. And again, we want to select some pseudopotential. So fetch PSP, and iron is some, let's use a different pseudopotential for a change. So here I'm going to use a built-in pseudopotential from DFTK. So maybe I should show the structure. So here is basically iron. And for this problem, we know that iron is magnetic, should be magnetic. So what we're trying to do is we're trying to do two kinds of calculations. So first, let's make the K-grid a little bit bigger, otherwise it may not work. And we're using LDA here with some temperature. We're setting up a plane wave basis. And let me just maybe show the result of this. I should probably use the structure from that I actually defined. There we go. So this is basically the iron computation. I selected a certain number of K points. The lattice now, because it's a magnetic and in particular also a metallic system, I selected some smearing, and the default smearing function is Fermi-Dirac. I can change this, of course. So for example, smearing equals smearing Gaussian if I want to. So now I'm using Gaussian smearing. Automatically it adds some entropy term, because now we're no longer minimizing the energy, but the free energy, in case you are aware of this. And now what we're doing for starters is that the default self-consistent field function actually does not apply spin. Okay, so this one here will do a spin non-polarized, non-spin polarized computation, which means that basically the resulting density here has no magnetism. But we all know that for iron, basically magnetism is something that is a thing, meaning that the actual lowest energy state is magnetic. And so the way one does this in DFTK is one actually defines some initial magnetic moments. And basically, when I'm constructing the model, I'm passing on the initial magnetic moments. And this will tell DFTK to use a magnetic and a magnetic setup, which allows one to get a magnetic ground state. So what we're doing here is we are again using the iron case. I should again use LDA. And I'm basically passing on the magnetic moments here as one of the arguments. And to make it comparable, I will keep using Gaussian smearing. And my basis uses the same K point and E cut. And this doesn't work because, because Pluto does not allow me to have two things in the state which have the same name. So let's give them a different name. Okay, so now we have another setup of iron, but the important point is that this should now be spin polarized, which we see here. So spin polarization is collinear, whereas up here, spin polarization is none. So basically, the first setup was not using spin polarization. The second setup is. And as a result of this, if we now start the SCF, we should get a lower energy solution because, as I said, iron has a magnetic ground state. So the magnetic state should have lower energy. Should use the right setup. And indeed, let's not talk about this yet. Same problem. And there we go. So first of all, you see that now it even tracks the magnetization automatically. The table up here did not have this. And we see the final state is indeed magnetic. And also if we just compare the energies, so SCF res no spin dot energies. And if we compare this with SCF res iron, energies, you clearly see that the no spin version is higher in energy than the spin version, meaning that iron indeed has a spin state, a spin polarized ground state, because the spin polarized state here is lower in energy. Okay, so the takeaway points here are, if you want to do a spin polarized calculation, you use magnetic moments, you pass them to the definition of the model. This makes the model collinear. And for example, you create a gas density explicitly that is also spin polarized. So this density here, if you inspect it, has size of the FFT size, so basically the basis that is used in the DFT computation, and 2. And the 2 is really the two spin components. So This would be the alpha spin density, and respectively the 2 would be this beta spin density. And I can also, there's also some convenience functions that, for example, then compute the difference. So this would be the difference of the alpha minus the beta, and so on and so forth. Okay, so far for the first few DFT computations, any questions? If not, I would move on to talking a bit about SCF algorithms, how to do customization of this in DFTK, and
Yeah, Jason.
For the smearing, are we allowed to play around and using different smearing?
Sorry, I understand hardly anything. Sorry.
The question was about, I think, other smearing methods that are available and potentially whether you can, how easy it is to make your own. General question about smearing approaches, I think.
So we have, I thought we somewhere even have a list. Okay, but definitely what we have is like Mathwell-Paxton of, I think, certainly up to order 2, maybe even arbitrary. Mazari-Vanderbilt, Fermi-Dirac, and Gaussian. And how hard is it to make your own? Where is my DFTK window? I mean, similar to the general approach of Julia, we are also following here some interface convention. So in the end, there's an abstract type called smearing function, and you're expected to implement the occupation, and you're expected to implement the derivative of the occupation. And with this, basically everything is done. In fact, actually, the derivative is even done by forward diff. So I think, I mean, there's no real formal definition, but I think if you just implement the occupation function, you should be good to go. So, no, the entropy you also have to implement. Yeah, so you have to implement the entropy function and you have to implement the occupation function. Those two you have to implement. And these others are optimizations for various functions. So here the Gaussian one, for example, this is probably the simplest you can possibly be. Yeah, so if you want, you have your own smearing, that's all you have to do.
Anything else from folks in the room? I don't see anything online. Just as a time check for you, Michael, we've got probably 55 minutes or so left. It's a lunch break next, so if we run a little bit over, not a big deal, but just.
No, that's great. That's absolutely perfect. I mean, I'm not necessarily expecting to go through everything, so it's fine. Right. We're doing very good. I also don't want to bore you, so if you're bored, then we can also just stop. Okay, so the next question is a little bit, how do you customize things in DFTK? So, I mean, I already mentioned that the typical way people solve these SCF problems is that they are, they follow this iterative scheme. So they look at the row at the n+1st iteration, starting from the row at the nth iteration with some damping and some preconditioning. That preconditioning I'm just going to ignore for now. And here we have basically the SCF step, the update function of building the new density, diagonalizing the Hamiltonian, and getting the new density back from that. And the nice thing in DFTK is that this particular function, sort of like this build new potential, diagonalize, get new density, this is something that DFTK exposes in form of this F function here. So basically, if you want to implement your own SCF algorithm, the only thing you really have to do is, to implement this loop here, right? So in this particular case, I want to iterate for a certain number of iterations. So I want to iterate for max eta this simple iterative scheme up here. So in practice, how do I do it? Well, I start at some density row 0. I have to apply to each row of n this function f. So basically, I'm going to compute here my f of row. So this one basically will do the real work. So this now really does the diagonalization of the Hamiltonian. And clearly, I will have to do this effectively at every at every iteration of my SCF. And how do I get the row n+1 here to at which I want to do the iteration? Well, this is going to be the row that I have. Then I'm going to have some damping factor. And then I'm going to have the application of the F to the previous row. That's essentially this guy over here. This should be a normal bracket. And I'm going to take the difference of this to the row I have, right? So this bracket here is basically this implementation here. And yeah, the rest I think is then fairly clear. Of course, we don't want to just blindly run this for a certain number of iterations. So what we are just going to do on top is we're going to have some stopping criterion. So if basically the change of the density at f of rho is like from the density that I put in, if this change is smaller than a certain tolerance, then I'm just going to break my iterations and call it a day. Right, so this is essentially underlying the idea here that at convergence, we need to have that f of rho is exactly equal to rho, right? So this kind of encodes that numerically. This is sort of the case. All right, so once we're done with this, we return the fixed point as the row, and we have a final check to see if the function is converged, right? So this is the interface that DFTK expects for functions that solve the SCF algorithm. Now with this, we can actually try it. So we take our favorite example, silicon here. So again, we are starting with a silicon, attach some pseudopotential information. And then what we're gonna do is we're just gonna make a new model. So model equal model LDA, let's say, or PDE rather. So from the silicon, this is what we did before. We're gonna discretize the model. Again, nothing too fancy. This is what we did before. Just gonna use very simple parameters to make the calculations fast. So this is by no way converged. If you want to do this for a practical calculation, this you need to definitely increase. So then we actually do our SCF. So we call self-consistent field. This is what we did before. And how did we do it before? Well, we called it on basis, right? So this was our sort of reference case. Now we want to improve this. So we want to well, not improve, but we want to use our own solver. So the way to do that is that there is actually a solver keyword argument. And so I can just use this interface here and pass it as a function. And then actually DFTK does some more internal tricks. So actually it has some internal damping parameter that is applied as well. So I'm going to set this to 1.0 just to make sure that we are really seeing what we're supposed to see. And now this was the SCF actually running with the implementation that I showed up here. And the nice part about it is because I actually made a slider that connects to this value, now I can actually interactively change the damping and see what happens, right? So here, this is with 0.6, and then this is with 0.9, and so on, right? So I now have actually not just some custom SCF algorithm, but I have an interactive custom SCF algorithm, which I could use to play around. And of course, what would also be very nice is not just to see this table, but to see it graphically. So let's see if I have plots. Yes, I have, very good. So the way to do that is that actually the SCF res object has something which is called history. So history, oops, what I wanted the delta row. Yes, so history delta row actually has the changes. So actually this one here, the change of the row between the individual steps. So that's essentially a proxy for the convergence. So I can just plot it. So it gives this thing, and then of course what I want to do is I want to use a log axis, and I'm gonna introduce a nice marker. and make the line width a bit larger. Give it a label, row, and there we have some nice SCF. And of course, if I now cut this up here and put it down there to make it a bit easier to play with. So now it all fails because I deleted the field. Okay, so now you see if I change it, my plot updates. And yeah, it's not as smooth as it is if you zoom out, but you clearly see that it's very nice and interactive to play with it in these Pluto notebooks, and you get some nice and instant feedback. And that's the reason also why I made the convergence parameters so crude, because of course, if the convergence parameters are higher, then this is not so much fun anymore. Okay, but one thing I wanted to also mention is it's not just that we have kind of cooked up our own SCF here.
We have a question in the room here.
Yes, please.
Yeah, go ahead, Ray.
From my output in the later semi-converged iterations, I get a bunch of plus signs next to the energy. What do they mean?
Yeah, let me see if I can reproduce this. No, not here.
But I did change the cut to 100, so.
You are very, very. You are living on the edge. Maybe we have it here. Anyway, yeah, I don't see it. I don't have an example, unfortunately. Maybe it will come up. So basically what it means is, so we are giving the change in energy and the change in potential in a logarithmic scale, because basically this makes it easier to track, sort of visually to track convergence rates and things like that. And the issue, of course, is when you take the logarithm of a number, you have to throw away the sign, which means that you don't necessarily see if the number, if the energy is increasing or decreasing. So what we do is that when the energy actually increases from one step to the next, we put a small plus. So that's what the plus means. Yeah.
Anything else while we're paused? Okay, nothing else right now.
Yeah, so the one thing I wanted to mention is that, so I don't have a GPU on this machine, so I can't show this. But in principle, if you want to do this computation, including your custom SCF, so right here on the GPU, the only thing you have to do is you have to add this one keyword argument, which basically makes DFTK put data on the GPU and run the calculation on the GPU. As I mentioned, this is not fast. So please don't do this for production. There's a lot that needs to be done, but I wanted to mention this and to show that the basic infrastructure is there. So in fact, in principle, the code runs on the GPU and is generic with the type of arrays that I use to do computation. But yeah, the performance, there's many details to get GPU performance fast, and that's we haven't really tackled. Okay. If there's no more questions, I would move on to the next bit.
I think we're good.
Great. So the next thing I wanted to talk about is a few things that basically both, mostly Timo, I think, already hinted at, but also Rachel mentioned. So of course, DFTK wouldn't really exist without Julia Molsim. I mean, we've basically already been using Christoph's nice atoms builder package to set up calculations. And basically in the other direction, Julia, DFTK can also be used as a calculator in various occasions. So, I mean, what Rachel mentioned with this ab initio MD, one of the things which I would really like to see is that you can just use DFTK and plug it into Molly and all of this boilerplate you don't need to see. I'm not sure how far we are at this stage. I have to admit, I haven't tried it recently. Maybe Joe knows if calculators already can be used in Molly to drive MD. If yes, then we would basically be there. If not, then I would say that's a great thing where us two should sit together and make it happen, because it can't be that difficult.
Yeah, they basically can, Michael. And there is an example in the Molly docs of using DFTK. I don't know anything about DFT, so it might not be that well optimized. But
yeah, I noticed that had appeared in the docs when I was putting this thing together. I decided to just keep the example I'd done before. But yeah, especially in light of the Adams calculators stuff, the way that I coded it up. That was before actually Adams calculators was, I think it was, maybe there was a repository, but it was certainly before there was much in it. And it might have even been before we started working on Adams calculators. So the way that I did it, it would actually be a lot, it might even be fewer lines of code now, and it's certainly less clunky. So that's a nice closing of the loop there for sure.
Great. We should definitely also have an example on this in the DFTK docs, because I feel, would be very good to show this. Anyway, what I want to discuss today is basically how to do geometry optimizations, because that's one thing that very recently got very easy with the help of Atom's calculator. So the starting point here is again an initial structure. I'm using aluminium here, a cubic aluminium structure with 4 atoms in the unit cell, and I'm rattling a little bit the structure. One of the things that at least last time I tried didn't work is that somehow units don't seem to work here. So it's just a memo to Christoph and myself to maybe figure out what's going on here. I noticed this on a demo a few days ago. So let's do it without units. The point is that nevertheless, you see I can get some small random rattling of the structures. And now the goal would be to use geometry optimizations to get back to the real structure. To the real in the sense of energy minimized structure. Now, how can we do this? So DFTK already brings an object called DFTK calculator that is really Atom's calculator compatible. So essentially, the parameters you would pass to a model, you put into one bunch of keyword arguments. The parameters you would pass to a basis, you put in another bunch of keyword arguments. And the parameters you would pass to a self-consistent field call, you put in a third. And based on this, you set up your calculator, and then this is already is basically ready and can be used in exactly the same way Atom's calculators should work. So, for example, I can just call potential energy on the aluminium and use the DFTK calculator for it, run some computations, and I get back the result. Or, for example, I can use the low-level entity and could, for example, call an energy calculation. Is this the right thing? No, it's not the right thing, right? Yes. Okay, and the nice thing is, as Timo said, we support a state. So basically, we support an entity that can speed up these kind of calls. So for example, if I do a second call like this, and I'm passing the state as the third parameter, then the computation converges in far fewer iterations, basically because it's now starting from the final set of calculation that was here, right? And why it needs a few steps and is not done in exactly one. There's a few details that are sort of hidden below the carpet. I'm happy to give you some insights why this happens. But at least you don't have to start from scratch. Particularly, that could be interesting if you now do the computation of the forces, where it will first do the SCF and then do the calculation of the forces, which are now available here, for example. Here are the forces, which are small. Interesting. So basically, it's not very rattled. So maybe I should rattle it a bit more to make it a bit more challenging. Yeah, that's better. It's still a bit small, maybe. Sorry, I'm just playing around with this to make it a not so trivial problem. Yeah, okay, that I can believe. All right, good. So now we have a system where we basically have non-zero forces, so something where it would be interesting to maybe try geometry optimization on. So here, the way we can do this is using the geometry optimization package that I have already loaded. So it's this package over here. And this directly supports a function result DFT, let's say, a function called minimize energy, which we in the live docs may be able to see how it works. So it basically minimizes the energy of a system using a system and a calculator, and you can also specify the kind of algorithm that is used to do the minimization. So yeah, it has a bunch of routines. So for example, using Optim, but it's also compatible with other solvers from optimization.jl. So for example, to just show you, I can use aluminium, and then I can use DFTK, and then let's just use geometry optimization.sim LDFGS. And then because I want to see what's going on, let's take verbosity equal to 2. And now it will actually run the geometry optimization, which takes a little bit. So it actually needs to run a few steps. I have no idea how many. So basically here it's the first step. So here's the maximal number of force after 1 second. Here's the other force. And the energy has gone down a little bit, and it's going down a little bit more, and even a bit further, and so on and so on. And after 5 steps, it's done. So what was the threshold? I don't remember. Somewhere it should say, I don't remember what the default threshold is actually. Anyway, yeah, so it's converged. And just to show you that we could really be quite generic here, so using NL session. So for example, there's a package called NLOpt, which is a C library for nonlinear optimization. So if I wanted to, for some reason, use this one, then I can just do that. Needs to install. I should have done this beforehand. Okay, so now it's done. And I want Newton. Let's use this one. And why does this not work? Ah, yeah. So now it's basically doing another geometry optimization, but instead of using the Optim LDFGS implementation, it just uses another kind of algorithm, right? And so, I mean, in principle, anything that is implemented by the optimization.jl library is possible. There are a few caveats. For example, some of the heuristic global optimization schemes, like things based on genetic algorithms and so on, they need a few more parameters that we don't set, but this is actually just a pull request away. So in case somebody would like to use genetic algorithms for optimizing his structures, this takes, I would say, about an hour of coding work. And in fact, actually, if you're curious and working on this, feel free to do it during the hackathon. Okay, any questions on this while this is running?
Go ahead, Lance.
Hi, Michael. So from the perspective of checkpointing, both in terms of geometry optimization as well as SCF, how easy is it to restart interrupted runs from where they were left off?
Yeah, that's an excellent question. So we worked actually quite a bit on this in the past. So tips and tricks or something. Yes, checkpointing. There we go. So basically the way it works right now is that you, like for actually DFT calculations by themselves, you have a mechanism where
Can
you
zoom this in just a little bit as well if you're gonna
yes,
use
of
specific
course.
code. Thank you.
You have something which is KW-args SCF checkpoints. So basically this takes a bunch of stuff and it transparently handles checkpointing by changing the keyword arguments for self-consistent field. So basically what it's doing is when you do this, it will transparently not use the initial guess density in case it finds a checkpoint. and it will do a few more things. In fact, actually, for example, we have some heuristics that determine how much the diagonalization will actually solve the bands, like how accurate the bands are computed. It will also update these heuristics. So basically, the only thing you really have to do is this. And with this, it checks if there is a checkpoint file. And in case there is one, it will continue pretty much exactly where you have left off. That is not yet fully implemented into the geometry optimization, I have to admit. So there's still some rough edges to make this work, but at least for standalone DFT computations, this is already available. Yeah. Again, if you're interested to work on this, I am very happy to give you pointers for some hackathon project. Yeah, I have some ideas how this could be done.
Else at this point. Okay, seeing nothing else, carry on.
Very good. Okay, so just to tell you, so NLOpt works. So NLOpt has also converged. The problem is with this optimization.jl is it tries to be generic, but then it's sometimes not. So for example, here it's for some reason it believes that it's still doing the 0th iteration and things like that. But yeah, there's not, and it thinks it's force stopped, even though it has actually reached convergence. Yeah, that's the thing with like stuff from Julia sometimes. Yeah, it works, in theory, it works nice. In practice, then there's all sorts of rough edges. Okay, yeah, so I think I'm gonna, so how much time do I have left?
About half an hour.
Okay, so I'm gonna skip the GPE part for now and move on to some AD. So what I want to do now, so this is actually going to be a fairly quick example, is I want to show you how to use algorithmic differentiation with DFTK to do something a little bit unusual. So here, what we want to do is we want to compute the band gap, how it changes as we change the lattice parameter of a setup. So basically, the idea behind it is, let's say we have let's say we have the following problem. So we just set up a silicon lattice, so an FCC lattice using DFTK, right? So we have some lattice parameter, let's say 10.264. And I did not include units. So this will then automatically update. And I'm going to set up a silicon element. So this is basically the low-level DFTK way of specifying a system. I specify the lattice vectors. I specify the silicon atom and basically with the pseudopotentials that I use to solve it. I say I want to have 2 atoms, and then I specify the fractional coordinates of the 2 atoms. And then out of this, I can make a DFTK model. So model LDA, lattice, atoms, positions. And then I get, similar to what we had in previous examples, I get a model here with LDA and the lattice setup, the atoms, number of electrons, and the respective terms. And again, I want to probably discretize this eventually to be able to solve it. So here I'm going to use the reasonable, not super great, but fairly reasonable setup. So here we now have a 4-4-4 K-grid. There's some symmetry, so actually we only need to compute 8 K-points explicitly. Then finally, I want to do an SCF res. So I want to solve the SCF problem, self-consistent field basis, and I'm going to use tolerance in the density of 10 to the minus 5. So this actually does the computation. And there we have the result. And now our goal is to, first of all, determine the band gap, right? So how do we get the band gap? Well, I mean, somehow we have to go through all eigenvalues. So actually, let me not redo this computation. So SCF-res has the eigenvalues. So the way this works is that there is one, this is a vector of vectors. So basically the outer layer is the k-point. So this will basically be the eigenvalues on the first k-point. This will be the eigenvalues on the 8th k-point. And on top of this, we have the Fermi level, right? So basically, if we take the eigenvalues at the first k-point and take away the Fermi level, then what we get is we get a bunch of elements, and at some point the sign flips, right? And so this means these guys are below in energy, below the Fermi level. These guys are above in energy from the Fermi level. So basically the conduction band minimum at this particular k-point here is just the minimum energy of all of these guys. So let me just write it a bit differently. So the minimum energy, which is negative, which is positive, excuse me. Right, so what we do is we compute an epsilon k relative. So there we just take this guy and we do minus the Fermi level. And the minimum of epsilon k rel, where epsilon k rel is larger or equal, greater or equal than 0. This gives me the conduction band minimum and the valence band maximum. This is basically the same thing where the eigenvalues are negative. So this is the conduction band maximum, and so valence band maximum. So if I take the difference between them, this is essentially the direct band gap at the first k-point, right? And so if I now do this over all k-points that I have in my SCF-res, so I can do this like this: eigenvalues to epsilon k. This then basically gives me all the direct band gaps, or the possible direct band gaps, and then clearly the minimum of all of them, of the gaps. This is the direct band gap of my problem. So this is a way to compute the direct, compute the direct band gap. And of course, I can very easily just paste this here and do everything in one go. And then I should not have multiple definitions, otherwise Julia complains. So here I do the SCF computation and I get the direct band gap. Okay, so now we have the first part. Now the final thing we need something to compute this derivative. Now, I mean, we basically already got 5% or 95% there, because now I just make this a function, silicon band gap. I start with some value for A, right? So this is now a function that, given a value for the band gap, for the lattice constant, computes me the band gap, right? So that means if I now use forward diff, you say derivative of the band gap function at this, and then unfortunately units, I don't think they work here. So let's do it without units. And then I compute it. Then it takes a bit of time because now it actually needs to compile the part of DFTK that depends on generic code in particular, the part that depends on dual numbers. So that takes the first time quite a bit of time. But the second time it's way faster, as I will demonstrate. And in particular, what I also want to do is I want to allude to the fact that we're solving a response problem. So we'll actually set the response solver to verbose. So let's try this. A bit confused why it takes so long, but maybe because it retriggered compilation because of this. Well. Maybe we have some questions. That might be not the worst time to take some questions. But yeah, now see, we also have the answer. So yeah, so just while you're getting ready for questions, so basically we set up this function, we're computing the derivative. So here it solves the standard SCF, and then it runs the required response problem to basically be able to compute the derivative of the density with respect to here the lattice parameter. This is essentially this GMRS here, so it needs about 4 iterations. Then this is solved. And that is used as an ingredient to compute the derivative of the band gap with respect to the lattice parameter. And there we are.
I don't have a question, but I'll just say I haven't seen that example before, and that's a really cool one. I see some appreciative nods, at least. Questions? Questions on Zoom? Spencer.
So you had to strip the units here, and I know this is like kind of a common problem with AD and a lot of the other more compute-intensive stuff is that in practice you end up having to strip units and then kind of add them in at the end. Is there gonna, is this the best that we're gonna have in Julia, or I mean, this is maybe broader than the Julia Molsim and what you're doing, but. It seems like a common pattern that we run.
Well,
into.
Okay, so there's two things to add. I mean, one is that so much of a problem, right? So I mean, when you have linear algebra, you don't want to have the units around. So eventually you will get to the point where you have to strip them. I think the only thing that is important is that one is able to handle these things transparently. Right. So one of the things that Christoph has pushed, and I'm actually in hindsight very happy about this, is that in Atom's calculator, for example, we have this concept of units that are attached to the calculator. And one of the reasons for having this is indeed to be able to say, well, okay, so in case you don't want to do all this fancy adding units back on and off and whatever. And in particular, if you want to do AD through all of these things, that each time you strip units and put them back on, that's a potential overhead. You can just sort of harmonize the units across your stack. And then you have some sort of a second interface, let's say, that is completely unit free. So in my opinion, that is the way to go. So ideally, you like at the user level, you definitely want to have units. So for example, ideally, when I call something like this, I want to see the units. But then as soon as I'm actually doing some real work, like let's say here in the self-consistent field or something, then I'm going to drop them, right? And I think that can be done transparently. I mean, not easily, of course. I'm not saying that's trivial, but I think there's some hope. If there's a way of the individual building blocks communicating to give a reasonable unit, then I think this can be done.
Yeah, I think I have some notes about things for the discussion time tomorrow, and I think kind of how we want to handle units across the ecosystem will definitely be a good topic for that. So far, we've been pretty adamant with just Atom Space that all of the interface functions should return units, and I think there was good reasoning for that. But as we talk about some of these more like interoperability type applications, where, as you say, there is going to be overhead for adding and stripping them every time, it probably does make sense to have an option for handing them around.
Yeah.
as long as you sort of have the guarantees of, you know, not ending up with any of these ambiguous situations. But if you're building kind of a bespoke workflow, that's unlikely to be the case, like the situation that you're in. So I think it's just a question of hopefully coming to some consensus about how to handle those somewhat distinct types of situations. And I think that'll be a good thing to discuss as a group tomorrow afternoon. Any other questions at this point? Check the Zoom again. Don't see anything, so got about 15 more minutes. Can maybe do one or two more. I don't know how long they'll take, but whatever.
Yeah, I think one more.
Great.
So in fact, actually, let's have a bit of a vote. So there's two things. I mean, I can either show you some really cool analysis of SCF algorithms that you can do interactively with DFTK, or I can maybe give you actually a tour of the code. So those were the two things that I still have in my head, like, you know, give a bit of an overview of the package, where things, how does it like work on the code side, something like this.
So at least for in the room, and people can participate on Zoom as well. I'll look for raised hands. If option one, sort of, I guess, the broad category of kind of mucking about with SCF iterations.
Yes. So kind of finding out what are like eigenpairs of the iterative matrix, and, you know, why do certain methods work in some cases but not in others, and so on. That's a little bit the one option, and the other option is to go through DFTK a little bit on the code level.
All right, so if you prefer that first thing that he was just saying around SCF stuff, hands up. All right, I see a couple people in the room here. Nobody on Zoom. Okay, and then second option being just sort of a tour of the code base generally. Okay, the room is overwhelmingly for option two. I don't think I saw any hands on Zoom one way or the other, so, but I think we'll go for option two. But it seems like option one, there's a notebook up there, so people, I think it's fair to say you can look through that yourself, and I'm sure Michael will be willing, whether it works out synchronously or not, but asynchronously, I'm sure he'll be happy to answer questions about things on the Zulip later on or whatever. So cool.
Yep.
All right, there seems to be decent consensus.
All right. So maybe given that we have some developers here, so let me mention that there's some very scarce developer resources and some very scarce details on, for example, how does our unit test system work? What are kind of recommended setups for developing, some conventions we use in the code, and so on and so forth. So I leave you to go through these in your own time. I don't think it's much point that I read the things that we already have documented. I think what's much better is that I kind of tell you things that are maybe not so much documented. So the rough structure of the code is, well, more or less the same as it probably is in many Julia packages. So the source that has the files, the tests, the examples, and the docs. I do want to spend a bit of time to go through the code, but before I do that, I also want to show some maybe peculiarities that can maybe trip people off. So our examples, for example, are automatically run also as tests, right? So if you put something here, it actually automatically increases coverage, for example, and if you make a mistake in the examples, then it will break the CI. So the reason for this is to make sure that actually the examples don't go out of sync, right? The other thing is that our examples, actually many of them are things that automatically put into the documentation. So for example, if I pick up this convergence study example, it actually is exactly the convergence study in here. And again, I mean, the reason for this is that typically when you have a nicely documented example, so here, for example, you see the run SCF and so on. And where is it? Here's the run SCF function, hopefully. The point again is, you know, once you've sort of gone through the effort of coming up with a good example, essentially this is something that already documents the code. So why not make sure that one thing that you do is automatically available for multiple resources? So that's something worth mentioning. The way this is done is that in the docs, we have essentially a small layer on top of the usual documenter, which if you basically give a JL file here, it will automatically run literate, and basically it is kind of smart in the sense that whenever you have something from an examples folder, that it will automatically sort of go back to the actual examples folder and pick up the respective files and process them. So that's essentially with respect to examples. So if you want to add an example to DFTK, put it here, put it also at the same time in the docs, and then it's available for everyone. We have some X modules. This is generally stuff that links outside of DFTK. So for example, we have some options that tweak with geometry optimization. So if you combine DFTK and geometry optimizations, some of the defaults are changed and things like that. That's done in here. There's some extensions, for example, talking to Vanier and so on and so forth. So this sort of stuff is here. On top of this, the tests, as I said, they also integrate with the examples. So and the test suite, for that one, we use something that is this well, what's it called again? Oh, I forgot the name, but it's like some fancy macro-based thingy, which actually gives some nice features to tag tests by names. What's it called? Test item runner. Yes, indeed. So we use test item runner, which has the advantage that you have these test modules that basically you can tag. And then in DFTK, when you actually run tests, you can selectively only run the tests of these tags, which actually turns out to be quite useful. And the way this is done is, I believe, described in the documentation, dftk.org. So test, most recent version, unit test system. So for example, these tags here, you can pass them, and then in this way, so no all disables the standard tests. And so in this way, you can, for example, only run the core tests, and for example, run the core and the atom space tests, and so on and so forth. And there's some more details how to do that. We also use this, by the way, to make sure that some tests only run on the GPU, some only run with MPI, and so on and so forth. So this is done at this level. Okay, so that's the high level structure. Let's go one level deeper. So on the level of the code, I think the most important parts are the terms. This is essentially where all the, essentially everything about the Hamiltonian happens in here. So you see basically the individual parts of the Hamiltonian, local energy, Hartree, Ewald, entropy terms, some more special things like for anionic systems, if you want to have magnetic things. Pairwise interactions, for example, are implemented for phonon-based things. And then basically the high-level Hamiltonian object that sort of assembles everything into something that you can, for example, apply to vectors and so on and so forth. So the terms really talk about the Hamiltonian, and they talk about the energy. And for example, just to give you one idea, in case you want to actually implement your own term, the way it works is that each term is expected to have a function called ini-ops. So this stands for energy and operations. So this essentially gives you, if you want, the energy term that is minimized in the DFT problem, and the corresponding first derivative of the energy, which will be a contribution to the Hamiltonian. So this is essentially what you need to drive DFT itself. On top of this, if you want to have one higher order derivative, then we come to the kernel. So the second derivative of the energy with respect to the density matrix or density. This is also a function that you can implement if you, for example, have, like here, you have a quadratic term in the Hartree term, right? So the point is that essentially it's again using very generic Julia tools, meaning that if you want to have your own term, you just implement the ini-ops, and you implement, for example, if you want a kernel, and then basically everything that DFTK can do, you can immediately use it on this term. So you don't need to modify DFTK in order to do that. That's something we do actually quite a lot for development. Okay, So that's the one thing that might be of interest. The other thing is the SCF. So SCF is basically this file. So the self-consistent field file has the main components. This, as you see, is a fairly big function, takes a lot of options. Many things can be configured. How much time should the SCF run? How many iterations? How many minimal iterations? And so on and so forth. And in the end, it's exactly this fixed point map that we used in the custom SCF. That's exactly this function here, which basically drives the SCF, as I said. So from a given orbitals, from a given density, it computes here a new energy in Hamiltonian. It computes the next density, basically goes through and does the SCF step, and in the end, for example, computes convergence, and then gives you the ability to talk to callbacks and so on and so forth, right? So this is essentially the main high-level driver of SCFs. And at various places, you have the ability to use arguments from here that interface and interact with the way the SCF is working. So for example, the typical solver that we use, so that's essentially the thing that I overrode in the second example that I showed, that is an Anderson acceleration-based SCF solver. If you want to have some other approach, try your own acceleration. This is, basically the thing you override. Then the mixing is the part that is this P-1, the preconditioning that I briefly mentioned at some point. There you have also the ability using a generic interface to supply whatever you want, really. And then, the convergence check can be completely changed as you want. And then there's many details, like how is the Fermi level determined, how many bands are used at each iteration, and so on. All of these, if you want, algorithmic building blocks are isolated out. And if one wanted, one could basically, or the eigensolver, which is used, same thing, could be easily switched if one really wanted to. So then there's a few other ways to do SCF. So we have, for example, a Newton algorithm, a second order algorithm, direct minimization. There's also an SCF which drives based on potential mixing. Ideally, all of these should be merged under one interface. That hasn't really happened yet for various reasons, mostly time restrictions. But again, some people are interested to work on these things. It's probably not the easiest task, to be fair, to start. But there's work to do for sure. Okay, that is the sort of the SCF and the Hamiltonian. That's like the main driving forces. What else do we have? There's some details on the eigensolver that I'm not going to show. Then there's some parts that we call post-process. So this is band structure computation, density of states, phonons, forces, and things like that. Then there's all sorts of details about the pseudopotentials, like, for example, how we interact with the pseudopotential libraries that are out there. That, like the pseudopotential IO, for example, a library to read standard pseudopotential formats. That is sort of this part. Response is basically everything that sort of deals with the second derivative of the energy. So for example, the independent particle susceptibility, that's the part where the Sternheimer solver Sternheimer equation needs to be solved. Hessian is basically as I said, the second derivative of the energy. So that's, anyway, these are really like low-level primitives that compute these individual aspects that take place when you need to solve a response problem, right? So I'm going to leave it at this stage. I'm very happy to go into more details in private discussion if that's something that people interests. Yeah, and then, I think this was basically the high-level tour. If there's more targeted questions at that stage, I think I'm very happy to answer them. But I feel that this is a good starting point or a good end point for somebody.
We're just about at lunchtime. Are there any other questions in the room or online?
I was just going to ask about atom space compact. So we had the recent atom space update version 0.4, how does DFTK play with that?
I didn't understand the question, unfortunately.
I think he
Joe?
was just asking, are you all the way up to date with
No,
atom-space
we're not.
compatibility?
No, we're not. Yeah, this was me writing a proposal, basically. No, I mean, we are on 0.3 still. Yeah, but there's the main issue is that we use other packages in the tests. So basically those need to go to 0.4 first. Yeah. But it basically, the main things that need to be changed is this function that passes the input data. It's not actually that much. Like in terms of actually the code that needs to be changed, it's not that much work. It's more that, bringing all the dependencies and interface packages up is the part that takes the time right now. Yeah.
Jason?
Is there any effort to go beyond just the plane wave and play with other data? This is one parameters, the first parameter is supposed to do this self-consistent field.
I didn't understand everything. The question was, is there the plan to go beyond plane wave DFT? What was another part to the
I
question?
think that was the gist of the question, yeah?
Yeah, plane wave.
Yeah. I mean, so first of all, like the way, like our code, the kind of algorithms we implement and the kind of heuristics we have, they work well for large basis sets. So for example, if you have Gaussian basis sets, quite a few of the problems and numerical tricks you would use are different. So it doesn't really make so much sense to implement, for example, Gaussian basis sets in this code. However, what would make sense, in my opinion, is to look at other large basis sets. So that means finite differences, finite elements, right? So this is something, I mean, at various places, we already have the basis generalized, right? This is by no means to say that you can right now use the code with another basis, but plane waves. It certainly wouldn't work. But in principle, the idea is that this should be possible, right? So yeah, I've been talking to some people, trying to convince them to look into alternatives. But yeah, it's I mean, many things would be nice, but then there's also a limit in time and people. But yeah, if somebody's interested to look into this, I'm very happy to give them pointers. I think it would be possible for sure to, like, for example, do finite difference or finite element.
Go ahead, Christoph.
A question for Michael, but also for everybody else. Any plans to go beyond DFT?
Me personally, right now, not really. In general, I would very much like that. I think there's a few very interesting questions. In particular, I mean, so I was talking about this whole business with response problems, right? So it's something where we invested a bit of time in the past. Basically, as soon as you have a fast response code, the next steps are time-dependent properties. And then, I mean, as soon as you have time-dependent properties, RPA is an obvious next step. So in that sense, building on top of DFTK to do these things, I think would be very interesting. And yeah, as I said, I mean, the codes, the algorithms, they can be used. I don't see this living in DFTK itself. I would more think of this using DFTK to make it work. So in that sense, very happy to work with somebody who is interested in doing that, not on the immediate agenda, I would say.
Yeah, I can just add as a broad comment for those not as familiar, there definitely are packages out there that are implementing beyond DFTK methods in Julia. I haven't looked in a while, so I'm not totally sure about the sort of state of maturity or sort of how actively developed they are, but there are things out there, and if people are interested, you can definitely dig around yourself, and I can point you to the ones that I'm at least peripherally aware of. So there are things out there for sure. I think we had one more question. Yeah, from Ray.
It's related, again, it's the interest of the future of DFTK, not in the, the method part, but, you skipped the GP part, which I was really hyped. And how much of the interest of people are interested in solving the general, like, nonlinear shading equations, and so what's the motivation for implementing the GPE part into DFTK?
The main one, I mean, okay, so it's again a good question. So what's the interest for implementing Gross-Berezovsky? Well, I mean, Gross-Berezovsky is like the little brother of DFT, actually. So from a numerical analysis point of view, a lot of questions that we are now finally able to tackle for DFT, the underlying techniques and mathematical methods have originally been developed for Gross-Berezovsky. Right? So the reason for having it is because this way you can actually step by step develop methods and scale them up. So for me, GPE is, of course, it's great that we can do it ourselves, right? It's nice, it's nice that we can do these computations. But for me, the interest is more that when you come up with a new idea, you come up with a new algorithm, Gross-Berezovsky is sort of the easiest nonlinear problem you can apply it to. That is sort of a step towards DFT, right? That's the reason for having it.
I think it's a very important feature to have, and beyond the quantum chemistry solid states, I work in ultra cold atoms, and solving GPE is a daily life.
Yeah.
It's good to have a performance solver, but it's a bit hidden under the DFTK's umbrella.
Yeah. Yeah, thank you for this feedback. I mean, to be fair, I mean, for us, as I said, we're not really like working on, I mean, the point is that in GPE, people have worked on a ton of highly specialized solvers for their particular applications, all sorts of things like vortex dynamics and what have you. I mean, I feel that really going all the way to make the code competitive in this regime would take quite a lot of effort and certainly expertise that none of us developers have. But for sure, I mean, we would be open. I mean, I think the code has a good basis for GPE. And yeah, in principle, one could probably do something. But I'm not sure if plane wave basis sets are the right thing to use there, to be honest, because usually it's confined problems. So probably for this one would certainly want to implement also a finite element or finite difference type approach.
Great. Well, thanks everyone for the questions. Thanks, Michael, again for kicking off this series of sort of deeper dive sessions. I think we're gonna break for lunch here until about 1:15. Thanks also for kind of throwing in some breadcrumbs about nice potential sort of next directions or hackathon things, pull requests. I definitely encourage other folks, if even if it just pops in your head during your presentation, or if you have some things in mind, sort of toss those out. Maybe someone.
I planned it all.
Sorry?
I planned it all.
Yeah,
no,
yeah,
not really.
exactly.
It was also very spontaneous.
Yeah, so I definitely, thanks for that example, and other folks feel free to do that too. Hopefully we'll have an active group of people hacking around on Wednesday, whether it's adding new features, or for maybe the newer folks, I think a really valuable thing you could do is like read through some of the docs for either these packages or Julia Mulsim things, and like tell us if things make sense. Tell us if you don't think you could have learned it just by reading the docs, because we really want to know that. So we'll talk more about all of this stuff tomorrow as well, but just sort of wanted to plant those seeds in people's minds. So yeah, with that, we're gonna break for lunch over here. I imagine for those of you who are sticking around from Europe, you might be breaking for dinner or something like that, and maybe you'll be able to stick around, or maybe it'll be time to log off for the day. But thanks again, Michael, for leading this and for tuning in.
Yes, it was a pleasure.
All right, and we will reconvene at about 1:15. Enjoy your lunch, everyone.